Welcome to this episode of Eureka. We are going to have a really wonderful and informative conversation with Professor Hirendra Ghosh. He is the Director of Institute of Nano Science and Technology, one of the youngest institute under the Department of Technology, Government of India. It's in Chandigarh. Before we continue this conversation, we are going to take a look at his brief profile. Keep watching Eureka. This episode is going to be really very captivating.
Nanotech is making its mark in the various sectors of science, be it health and medicine, electronics, energy, environment, and even in space. Its applications are numerous. It is where Professor Hirendra Ghosh has extensively worked. Currently, Professor Hirendra Ghosh is the Director of Institute of Nano Science and Technology in Mohali. Born in Domboma village in Birbhum district of West Bengal, Professor Hirendra Ghosh completed his MSc in Chemistry from IIT Kharagpur in 1989. Later on, Professor Ghosh joined Chemistry Division in Bhabha Atomic Research Center in 1990 after successful completion of BARC Training School course. Professor Ghosh has obtained his PhD degree from University of Mumbai in 1996. He did his postdoctoral studies at the Chemistry Department of Emory University, Atlanta, USA in femtosecond infrared spectroscopy during 1997-1998. He has developed femtosecond pump probe laser spectrometer detecting both invisible and infrared region. His current research interest includes ultra-fast interfacial electron transfer and charge carrier relaxation dynamics in semiconductor nanoparticles, hybrid nanostructures, plasmonic and 2D materials, and using different ultra-fast techniques. He is also involved in design and development of quantum dot solar cell and photodetector, also actively investigating mechanisms to improve the device efficiency through ultra-fast spectroscopic techniques. Currently, he is also involved in developing pump probe femtosecond terahertz spectrometer. Dr. Ghosh is bestowed with various national and international recognitions. Noted among them are INSA Medal for Young Scientist, CNR Rao National Prize for Chemical Research. He is also fellow 3 major Academia of Sciences.
Thank you for being with us. It's a wonderful experience.
Thank you.
We saw some of your labs, the kind of problem that you want to tackle. They all seem science fiction. I mean, it's like you are in one of those science fiction television movies where people talk about gadgets which are of futuristic. So let's start with some of the fundamental questions about nanoscience and technology. We talk about nanoscience, but nobody talks about kilometer science, meter science, millimeter science. So how does this nano becomes important?
Well, when the size of the materials, say for example, I'll tell you particles, comes in the nanometer, 10 to the minus 9 meter size, the properties of the material or particles is much more interesting than when particle size is bigger. The main reason is that in that case, most of the atoms which make a particles, they are almost to 70 to 80% of the atom comes on the surface. So that's why you can get a very exotic properties which can be application oriented, and you can a lot of fundamental also issues will come to the picture, and you know many things which actually people do not know. So you talk about one nanomaterial and you studied many interesting properties, you change the size of the particle, you can get a different properties.
I see. Okay.
So that's the main reason like why people are crazy for nanoscience.
Can we give an example of where just by changing the size, the property of the material completely changes?
Okay, let me tell you, if you take about simple semiconductor material, cadmium selenide, which is basically a direct band gap material, and the material has its own Bohr radius, it's like around 6.3 nanometer. Now, if you synthesize a particle of 6.3 nanometer, you can tell it's a quantum dot. Now, if you bring down the size of the particle, then strong confinement will take place, or if you increase the size, then it will be weak confinement. Now, what is the difference? When you increase the size of the particle, the band gap is actually decreases, and also confinement level also decreases. So optical properties, luminescence property completely changes. On the other hand, the same particle, when you bring down the size, your confinement increases and band gap increases. So how does it make the difference? See, it absorbs different portion of the solar radiation and it also emits different color. The same material, just by changing size, you find all different colors. That's the exotic properties actually. That's the main reason this kind of semiconducting quantum dot material are highly application in solar cell, photodetectors and many other applications, even also biology and medical application you have.
Okay. One of the area that you fell in love perhaps when you were very young was laser spectroscopy.
Yeah. Well, I did my master's in IIT Kharagpur and my specialization was physical chemistry. So actually the main book actually, textbook of physical chemistry I used to read P.W. Atkins. And my most favorite subject in the physical chemistry was spectroscopy. Now in that book what I observed, like that time like 1987 or 88, laser spectroscopy already it has come in the world, but not in India, it was not very much. So there it was told that any kind of chemical reaction which takes place in very, very fast time scale, actually you can monitor the reaction. So during the electron transfer, proton transfer or energy transfer process, actually you can monitor the structure of the molecule, structure of the system and also monitor the reactions. For that you have to use a short pulse. During that period of time, short pulse used to think out only picosecond, but later on it came femtosecond and now attosecond people are working.
Something like femtosecond you said.
Yeah.
What will be its size? I mean like how much part of a second?
10 to the minus 15 second.
10 to the power of minus 15. So it means that I divide 1 second into crore parts
yeah.
and one of those parts. That's a kind of time that you are talking about.
Yes.
I mean something that one can never imagine. Like.
Not imagine actually.
Yeah, very interesting. So now you fell in love with laser spectroscopy and then you built your own laser spectroscopy.
Yes.
Right?
So I actually my early career, research career, after my masters, I joined in Bhabha Atomic Research Center and I had a 1-year training school program. And after that I joined in chemistry division. And most interesting part of in BRC during that time, like you will not be given any instrument, you have to build an instrument. So I joined there and started learning how to build a laser spectrometer, and that's the first learning things we did. And that time I think we did work on nanosecond and picosecond laser spectrometer. We built it and we completed our PhD. So during our time, first you have to build your own equipments or instrument, then you have to do research, and then you have to publish paper. So things are completely changed these days.
Okay. So I mean, but that kind of experience of building your own instrument gives you a much more depth into the issues, right?
So the thing is that when you build your own equipment or instrument, you can change the system such a way. Suppose you are monitoring some chemical reactions, ultra fast reactions, and the commercialized system actually cannot give you all the answer. Suppose you want to change the color, change the different angle, different overlap, all kind of jargon is there. You really cannot understand if it is a ready-made system. But when you build your own system, own equipment, actually you can maneuver the equipment such a way you find the best property of its ultra-fast processes, whatever thinking about.
Okay. So when we talk about this laser spectroscopy, one is of course laser, the other word is spectroscopy. Laser is basically the light with which you want to excite some material, right?
Yeah.
So then you want to excite some material and then you want to see after the excitation the kind of wavelengths in which that material is re-emitting the energy, which you want to study in a spectroscopy.
Yeah.
So spectroscope, the way we would have studied in school is you can find various elements.
Yeah.
So when you are talking about chemical reaction, we are talking about molecules. So, but just by knowing that water has hydrogen and oxygen, I don't understand water, right?
Yeah.
I need to understand the molecule. How does a spectroscopy help that?
Well, spectroscopy, there are many analytical tools as there where you can tell that, well, if you use, you want to know about water, you use infrared spectrometer, you will find a OH band, some 3500 or somewhere, broad band you will observe. Now, say for example, you want to see the excited dynamics of the water molecule. Suppose you excite the water molecule, what is happening to the hydrogen and oxygen? So then you have to work in a mid-infrared spectrometer which can monitor the reactions in femtosecond time scale.
Okay.
So for that matter, I build a spectrometer where you can excite the material in like 200 nanometer or 300 nanometer, and then you can see the vibration band moving around, and you can see the changes in the excited states by you put a laser light, you go to the excited state, and then you give a probe light, and actually the excited state process you can monitor through pump probe spectroscopy. That's how you can do that. This is a very simple example I am telling.
Okay.
But the kind of research I am doing here, this is completely different, which is basically I am working on solar cell. Two type of solar cell actually I have worked. Earlier I worked in dye sensitized solar cell. Now I am working on quantum dot solar cell. In dye sensitized solar cell, like you have titanium dioxide, and then you have a dye molecule, and then you excite with the solar radiation, you go to the excited state and inject electron. Now this process takes place in femtosecond time scale, less than 10 femtosecond or so. So you have to monitor the process such a way that if you know the mechanism, then only you can improve the efficiency of any devices.
So what you are pointing out in sum and substance is that there are not just one kind of spectroscope of the ancient era, that now we have a range of spectroscopes,
so many range of
different.
Yeah.
That's an interesting point. With this, we'll take a very, very short break. Keep watching Eureka. After the break, we are going to talk about his work on solar cells. Keep watching Eureka.
The Nehru Trophy boat race of Kerala, popularly called Vallam Kali in local parlance. This historic boat race dates back to 1952, when Pandit Nehru visited the state and a pageantry of boats accompanied him from Kottayam to Alappuzha. The race, conducted on the second Saturday of August every year, is a major tourist attraction. It's generally the snake boats which participate in the race, and hence the shape of the winner's trophy is also a replica of a snake boat.
Before the break, we were discussing about your work related to laser spectroscopy and how you build laser spectroscopy, and then did quite a bit of work in looking at mechanisms or reactions taking place in shorter times, like picoseconds or femtoseconds. Let's look at the name of your institute. The name of the institute itself is Institute of Nano Science and Technology. When you say science, it means that there are questions for which we don't have answers. There are puzzles. So which essentially means there are some puzzles which the nanoscience is trying to address. What are the unknowns, for example, which the nanoscience is trying to address?
See, let me tell you, if I start the work which I am carrying out, solar cell. Now, let me tell you, like people think about solar cell means silicon solar cell. And silicon solar cell is good and widely available in the market, and people are using it. And but why we are thinking another solar cell? The reason is that silicon solar cell, when you use it, the amount of energy is required to build the solar cell. You need 7 years of solar radiation to have the energy balance.
So you mean to say that, for example, if I put a 1 megawatt solar plant, I would have actually spent something like 7 megawatt energy in producing it. So I get back it in 7 years. Only after that, actually, I am producing the energy.
Exactly.
Okay.
So that's why scientists are thinking like where you put less amount of energy, still you can get a very good solar cell, high efficiency solar cell. So that's why solar cell or dye sensitized solar cell, quantum dot solar cell come to the picture. Where I have done my research work last 15 years. First, let me tell you what is dye sensitized solar cell and what is the importance of nanoscience. As I was telling that once your most of the atoms or molecule on the surface to volume ratio is very high. So the solar radiation comes here, it absorbs more solar radiation, and you can get higher efficient solar cell. If the particle size is bigger, then your absorbability of the same material will be much, much less. So, we talk about a dye-sensitive solar cell where nano porous Ti2 materials, and on top of it some dye materials we use, and then make a solar cell, and what are the protocol you follow. Now, the question is that to increase the efficiency of the any kind of devices, I am talking about dye-sensitive or quantum dot solar cell, you need to know the basic fundamental reactions, which is basically talks about nanoscience.
Okay.
So, what are the basic fundamental sciences? Like when you, solar radiation falls on molecules or quantum dots, it goes to the excited states.
Yeah.
And the excited states, it inject electron in the electrode, Ti2 for that matter. And that process is extremely fast, ultra fast. That's why we are talking about this femtosecond laboratory, and that's what we are doing it. Now, this science can only be possible if you want to, if you do a fundamental basic science on nanoscience.
Okay, okay. So, only after understanding this, we will be able to make a better choice of it. That's an interesting thing. Now, let me come to your major work that you are doing right now, which is your interest is to increase the efficiency of solar cell or come up with a new generation.
New generation solar cell, correct.
So, what are the basic questions that you are trying to address in this new generation solar cells?
Yeah. Well, right now we are doing like quantum dot solar cell, and in quantum dot solar cell, like you have a quantum dot material, you give a solar radiation, you create one electron hole pair.
Okay.
Now, why people are crazy about quantum dot solar cell? In case of quantum dot solar cell, when the band gap is low or confinement is little weaker, then what you observe that solar radiation comes, instead of one electron hole pair, it can create multiple electron hole pair.
Okay.
So, one photon can create more than 2 electron hole pair. So, as a result, your efficiency can be improved. Now, these processes, absorption of radiation and exciton generation and dissociation of a bioexciton, these processes are very, very fast. So, that is why we really need to understand.
So, something like, for example, if in a simple term one has to understand, in a quantum dot solar cell, with one stone you can get 2 mangoes.
Exactly.
That's a kind of thing that you are trying to find out whether you can do it. Fine. What challenges are there when you are trying to build such a thing?
Challenges are multiple actually. First thing that the stability of the material is a big issue. I mean, these days actually people are working on perovskite. I am also working on perovskite. Perovskite solar cell, its efficiency is coming like 22-23%. But the problem with the perovskite solar cell that stability is very poor, particularly in presence of water vapor. Okay. So, when you make a cell in presence of water vapor, the stability is so poor, in a day it will be destroyed. So, that is the one big trouble we are facing for this kind of quantum dot materials, the stability of the materials.
So, one is looking for a material which will be stable in actual natural conditions that exist outside in the real world, right?
At the same time, the material which absorb visible and near IR radiation, and it can most part of our solar radiation can be used for your solar cell application.
Okay, very. Another area of your interest is this fast reactions, studying fast reactions. So, you have also developed photosensors.
Photo detectors. So, I am working actually, I am working on photo detectors. If you see in the market actually, photo detectors are visible, infrared, near infrared, all kind of different kind of photo detectors available. So, we are working on a materials where in one single material can be used for the entire visible to near IR to infrared. We are working on kind of semiconducting copper sulfide material where the material copper sulfide or copper selenide, you create vacancy and it can get a broad absorption band, and that can be used. So, those ultra fast processes is completely unknown, that is what we are working. So, if we know these processes, how fast actually the photon can be detected, then we can make a better devices photo detector.
So, same detector can detect in multiple ways.
Multiple, the entire region from visible to near IR to infrared.
Thank you. I mean, this is where we will take a very short break. After the break, we are going to discuss with him how his institute is going to use nanoscience and technology for developing novel mechanics for wound healing, to developing new drug delivery systems and developing innovative materials. Keep watching Eureka. After the break, we will continue this conversation.
Rabindranath Tagore was awarded the Nobel Prize for Literature in 1913 for his book Gitanjali. In 1950, he composed the music and lyrics for India's national anthem, Jana Gana Mana. And when Bangladesh became independent in 1971, they chose Tagore's song, Amar Shonar Bangla, as its national anthem. Tagore's life and works have made him a cultural icon, studied the world over, even into the 21st century.
Welcome back to Eureka. We are having a very wonderful and very informative conversation with Professor Hirendra Ghosh. He is the director of Institute of Nano Science and Technology, an institution under the Department of Science and Technology, Government of India. I want to ask you another important question. I mean, in your laboratory where you have this laser spectroscopy, you are trying to work on materials and trying to detect how the holes and exciton pairs are formed and how they change, and one of the major challenge is this concept called trions and how they decay. Can you explain us some basics of this first of all?
Yeah, let me tell you, this research recently we have discovered. We are working on molybdenum sulfide, monolayer deposited on silicon dioxide surface, and then actually molybdenum sulfide is a 2D material, and this is a very widely applicant material. And when the molybdenum sulfide is a single monolayer, then it behaves like a semiconductor.
Okay.
And when it is multiple layers is there, they don't behave like a semiconductor, indirect band gap. Now, when we use this monolayer semiconductor and excite with a laser spectroscopy, laser light, then what we observe, electron and hole pair created.
That's
so
a
that
normal
is
thing in
that's the
any,
normal things in any semiconductors.
Yeah.
Now, in this case, what happened? Because it's a 2D monolayer, so electron actually mobility is very high. So sometimes once you create electron hole pair, it takes some time to form exciton. Exciton means electron and hole pair together we call exciton. Now, before forming exciton, one of the electron will lose out from the hole.
Okay.
Now, that electron can bind with another electron hole pair which already formed exciton and form trions.
Okay.
This is one of the fundamental physics particle, and actually we are working it, and we are very, very excited talking about the ultrafast spectroscopy of the trion.
See, what is the problem with the trion? I mean, in a semiconductor, if more trions are formed, what happens?
No, actually it is not good for any devices. Because trion formation means it binds two electrons. Actually, the electrons are holes you want to use for different kind of application. Now, if the electron gets stuck in somewhere, some kind of physics particle, then actually you cannot really use it properly. So, in that case what happens, you have to see how trions are formation and how can optimize your system so that trion formation is less and you can use for your better application. So, one of the things we are doing, like we put gold particles where gold can actually accept the electron whatever you are forming. So, what we observe, before putting the gold, we found that trion formation and decay of trions, they are like 5 to 6 picosecond, and then it decays another some 100 picoseconds. But in presence of gold and nanoparticle, if you put it, it takes care of all the electron. So, you do not see in trion formation.
Okay,
so, this is in a real devices, when you MOS2 and gold come together, it is very difficult to.
So, you can completely suppress the trion
suppress
formation.
it might not be completely, but it is possible to completely suppress the trion. If you make a bigger gold nanoparticle, more accepting states will be there, it can take it.
Okay. So, this kind of a research, where does it lead us to?
Well, this like understanding fundamental particles, it has a solar application, photodetectors, all kind of things what we are talking about. In many times, trions might be forming, but we do not know, because you should have a proper spectroscopic technique to understand the basic mechanism. That's why we are doing all this nanoscience in this institute.
Very, very interesting. Now, let's come to some bit about the institute where you are right now.
Yeah.
I mean, this institute, what are the major kinds of activities, major research program that you are embarked in?
Other than a solar cell or photodetector, what we are talking about, we are also working on water splitting, hydrogen generation, And also we are working on electronic material made of carbon actually, graphene. And also many of our faculty are also using for healthcare like nanomedicine, cancer research, and also wound healing research.
Wound healing, that's very interesting. Where does the nanotechnology comes into wound healing?
Yeah, I mean, look, when the particle size is nano, one of our researchers, she is doing some research on wound healing and wound management. So she has discovered some material where, suppose if you get a gunshot and the blood will be coming, very fast. So if you put that material, it can actually clot the blood properly.
Okay.
Yeah. So these are the research actually we are doing wound management studies.
Okay, that's a very interesting thing. You are talking about using nanomedicine. I mean, something in nanomedicine, right?
Yeah.
So what is the kind of areas that people are looking?
Where our scientists are working, many of them working are cancer research, where they can give a targeted drug delivery. You can kill the cancer cells separately, not the normal cell. So different kind of nanomaterial they are generating and doing all kind of fundamental research, and they are doing it. A big group is working in cancer.
So what kind of new materials that your institute is focusing on using nanoscience and technology?
New materials like one of I was telling carbon material, graphene, and also we are working like in my group we are doing all kind of semiconductor quantum dots, and other people are doing like iron materials, iron nanoparticles, and other metal nanoparticles, gold nanoparticles. They are also working, and many 2D material people are doing all kind of 2,6 semiconductors and 3,5 semiconductors, all kind of materials they are using.
Very, very interesting, and I think if you visit this institute, you and look at the kind of work they are embarked on, they are all futuristic. It looks like science fiction. In India today, nanoscience is the third largest contributor of published scientific publication, and India is one among the top 5 countries in nanoscience and technology. With your institute's input, I am sure India can go to heights. We have had a very, very interesting and very excellent talk and conversation in this episode of Eureka. Thank you for being with us in this show. Keep watching Eureka. We will come back with a very interesting conversation next week.